So I updated the notebooks and added a few files for what we'll be doing today to the Dropbox folder. So I'll just give you a minute to update all that. And I also uploaded underscore work IPython notebook, which is what I was working on yesterday, because you will need to kind of merge together the notebook you were working on yesterday and the edits I made to the skeleton later. So that will be a little bit cumbersome. So you might want to just start by loading up that underscore work notebook. So from the Dropbox. And what we'll do is, as we are recapping what we did yesterday, we'll just quickly run through the cells of the code that we've already written. And that way all the variables that we loaded yesterday and whatever calculations we've done up to that point are accessible for what we're going forward. So I'll give you a few seconds to sync everything from the Dropbox, and then we'll get started. So what we're going to do today, we had done up to electronic band structure yesterday. We are going to use the same formalism to compute electronic density of states, and then the dielectric function due to direct optical transitions in the material. After that, I changed the plan a little bit from what the outline said here yesterday. We're going to look at the Phonon band structure and density of states in the same way, using almost the same code, so you'll see how general that is. And then in the last part, we'll work on electron phonon matrix elements, and we'll predict the temperature-dependent resistivity of aluminum from first principles. So hopefully we'll get up to that point, but in any case, you'll have the notebook and you can finish up if we fall short of time. So was everyone able to load up the work notebook and synchronize all the files? General show of hands. All right, great. So, so what we started with was examining the cell map file. We looked at it in integer lattice combinations and Cartesian coordinates, right? From that, we figured out that we could determine what the basis of lattice vectors are by solving this least squares problem. Inverting that matrix gave us the reciprocal space basis. Then we read and reshaped the Wannier Hamiltonian to this, the number of cells, which is telling you the relative displacement in terms of unit cells between matrix elements of the Hamiltonian. And then for every Wannier function in one cell and every Wannier function in the other cell, you have a matrix element, right? So we wrote that in. Then we loaded up a high symmetry k-point path, which consisted of points that are on those vertices or edges of the Brillouin zone, labels associated with them for the band structure, and how many points to put together. Right? We loaded that up, and then we constructed the k-point path, which we would use for the band structure. And then finally, we looked at Fourier transforming the Wannier Hamiltonian to points along that k-point path, diagonalizing it to get the energy eigenvalues. We showed that we could vectorize that much more easily just using how the eigenvalue function in Python is vectorized. And so you can do that in a single shot and not have to loop over k-points. And then when you plot that, you get the band structure. Right? And we just cleaned up the plot a little bit, and that's where we had stopped. Right? So any questions up to that point before we move forward?
Could you please explain a little bit what is H-Wannier?
H-Wannier, yeah. So as we had discussed briefly in the slides, every physical operator that you have, which is going to be an expectation value between two wave functions in block space, can be transformed via the unitary transformations to be in the basis of Wannier functions. Right? So it's effectively the Hamiltonian, which corresponds to the energy operator in the space of wave functions, which has been unitary transformed into this localized basis. So it's effectively in a basis of Fourier functions. It's telling you if I take one Fourier function which is there at one location, I apply the Hamiltonian to it, I will get some wave function, and I take the overlap of that with another Fourier function, which could be not in the same unit cell but in a nearby unit cell. So the H1A is storing so I have a certain number of Fourier functions in each unit cell. It's telling me for every pair of Fourier functions for all neighboring cells what that expectation value is.
So is it from the DFT calculation?
Yes. So you start from the DFT calculation and you have the energy eigenfunctions and eigenvalues. You do this unitary transformation to construct this object. So when you construct the Fourier functions, you're getting this unitary transformation between your original wave functions and these localized functions. And if you apply that unitary transformation back onto the original DFT Hamiltonian, you get the Fourier Hamiltonian. But the idea is that this Fourier Hamiltonian now is much more compact because it has been projected down onto the Fourier functions. The original DFT Hamiltonian is an operator in a fairly large space, right? You take your wave function in a plane wave or any other basis, and you can evaluate what the kinetic energy is and so on, right? All of that has now been summarized in this Fourier basis. Okay? So just to make that a little bit more concrete, if you were to, so you could also write the Hamiltonian in the basis of eigenfunctions that you have from DFT. That is, you have these orbitals and eigenvalues that you get from DFT. If you were to write the Hamiltonian in that basis, it is just a diagonal matrix which is equal to the energy eigenvalue at each eigenfunction. Right? But what we want to be able to do is to calculate that property at any arbitrary k that we are deciding to use. So that's why we first go into this localized space such that we can do this Fourier transform back and calculate it at any other k point. Right? So we have already done that. So the k's that we used here had no connection necessarily to the k's that were used in the DFT calculation. Right? So we can produce this band structure with arbitrary resolution in k, independent of what k points we used in the DFT calculation. And as Natalia was asking, maybe towards the end of yesterday, that's one of the reasons why this is used just for band structure interpolation when you have a very expensive electronic structure method where you cannot afford to do this at sufficient k points to generate a band structure like this, like in GW. Any other questions? Okay, so far we've been working on this high symmetry path, and as I emphasized yesterday, this is primarily for visualization, right? We have k points going all over this three-dimensional space, and representing it all over that space would be very difficult on a plot like this. That's why we chose this unraveling of a specific k point path. When we're doing the calculation of any physical property, you have to integrate over that entire Brillouin zone. So when we go next, for example, when we're calculating the density of states, we won't use the high symmetry k point path anymore. We will integrate over all k points in that Brillouin zone. Now, so first let's start with the definition. So the density of states is basically measuring how many states are available at a given energy per unit volume, right? So to calculate that, I could just go over all k and band values and just sum up these delta functions. So that will measure how many of those states correspond to a particular energy, and I'll get a function of energy, which is the density of states, right? And this GS is the spin degeneracy factor, so it will be 2 in our calculations, and you divide by the unit volume to get the density of states per unit volume. All right. So the first thing we need to do is to calculate the unit cell volume because we're going to need that. So this is once again just for warm up. So can anyone help me with that? Based on what we have so far, how would you calculate the unit cell volume? Right, so we have the lattice vectors. And how do we calculate the volume from that? Because this is not a cubic lattice. The unit cell is not a cube. Right? The unit cell has some odd shape associated with 3 lattice vectors, which we had over here. These are the columns of those correspond to our lattice vectors. So if you want to calculate the volume of the parallelepiped that emerges out of those three vectors. Very good. I already have this as a matrix. Is that an easy representation in terms of the matrix? What you're saying is exactly right. And suppose you were to do the same thing in n dimensions, what would the situation be instead of 3? It's just the determinant. It's just the determinant of that matrix. And so that would, so the triple product that you have is just the determinant in the case of 3 dimensions. Right. So what you would have here is and the only thing we will take the absolute value because we don't care whether it's left-handed or right-handed for this particular case. Right? So that would be the unit cell volume in Bohr cubed. Okay. All right. So now let's jump from that very simple thing directly to the density of states calculation. So what we are going to do is we need to calculate an integral over the entire Brillouin zone. Now if you remember, you might be worried about how are we going to do an integral over that weird shape that we were showing yesterday, right? So the important thing is all the properties that you get here are periodic in K. So the reciprocal space has a periodicity given by the reciprocal space basis that we had, right? And what the shape you were seeing, the Brillouin zone, was just the unit cell of that lattice. So it's conventional to represent the quantities there, but when we're doing the calculations, we could do the calculations over any unit that tiles and covers reciprocal space, and it doesn't have to be of a particular shape. So the most convenient choice is to actually pick the unit parallelepiped that goes along those reciprocal space lattice vectors, which in the fractional units that we are working with just corresponds to taking k going from 0 to 1 in all dimensions. Right? So basically, if I account for the non-orthogonal lattice vectors in terms of the basis, in fractional coordinates, all I have to do is take each coordinate from 0 to 1 and cover that one parallelepiped, and then automatically that is equivalent to integrating over that complex shape because of the periodicity. All right? So in doing this in Monte Carlo sampling, all I need to do is create random numbers from 0 to 1. How many ever points I choose, let's say 1000. And there are 3 vectors to cover the 3-dimensional Brillouin zone. Right? So this would be a Monte Carlo sampling that would cover exactly my unit cell. Now I need to compute the energies, which I'll do exactly as I did for the band structure. So I'm going to copy over the code from here. With the only difference being that instead of using the k-point path, I will do this using my Monte Carlo sampling of k-points. All right? Now, and I don't need my unitary transformation, so I'll just drop that. So in Python, if you just put that underscore, that means neglect that output. And you'll see me do this often. So the other way I could do that is this returns a list, so I can just take its first element and neglect the rest. So all of those are equivalent. Okay, so now I have a list of energies. I need to do this computation. So let me focus just on the sum first. Summing over these delta functions is basically equivalent to histogramming. It basically says I have a grid of energy eigenvalues, and each epsilon kb that I encounter, I put in a particular bin, depending on its energy. Right? That's basically what this delta function is doing. So I'll just use the histogram function to do that instead. Right? And this originally had a dimension of number of k points by number of bands. I'll remove all that information. So I'll just give it a flat list of energies because that's all I care about. Right? And I've created this energy grid to work with. So I will pass that into the histogram function. And again, it gives multiple outputs, so I'll drop all the remainder. Now, this is giving me a conventional histogram where I'm just counting how many states happen to appear within each bin. I now need to normalize it and convert it to a probability density. So the first thing is I have to divide by dE to convert from a probability to a probability density, and then I need to account for these factors. So effectively what I will do here is multiply this by 2 divided by the number of k points, unit cell volume, and dE. Right? And this dE factor was not present in the expression, but that's basically the relationship between taking this delta function and converting it to a histogram. Right? Also note that the delta function has the dimension of 1 over its argument, so that would not be accounted for in the histogram by itself. All right? And then we can plot that, and this is what we would get. Sure, yeah. Yeah. All right. So effectively, we just histogrammed and then accounted for normalization factors to calculate the density of states. And the only change in the Wannier part of it was, instead of working with the high symmetry k-point path, we use this Monte Carlo sampling over the Brillouin zone. Now, of course, because we're doing Monte Carlo sampling, this result is going to change every time we run it. Right? Because of a new random number seed. Now, clearly this is not enough sampling. We need to increase the number of k-points to get good resolution here. So I could simply go and start increasing this, but and you'll of course reduce the error that you get here because you're getting a better sampling. But if you wanted to do more expensive sampling, or we just wanted to go for more k-points, very soon we'll not know how long we're waiting, so it would be good to rewrite this in a way where we actually know how far it's gotten and how long we have to wait, right? Secondly, if I keep increasing this number of k-points, I'm doing this vectorization here, right, where I'm computing a large number of k-points together, and it is extremely important to do that vectorization when you're writing Python code, right, because there's a heavy cost of the interpreter. So if you write everything in a loop, you're going to get a significant performance disadvantage. But if you vectorize too much, there is a disadvantage to that as well. Any thoughts on what that might be? So when you're writing Python or MATLAB or equivalent code, you have to vectorize the code so that you don't have an interpreter cost, right? But suppose you vectorize too much. Suppose you're working, instead of doing this, so let me say if I were to profile this code and I was doing this by looping over every k-point individually, or doing vectorized over 100 k-points and then looping and so on, right? I could trade off between how much I'm looping and how much I'm vectorizing, right? Now I'm saying that there's actually a sweet spot. It's not that the more you vectorize, the better. Any thoughts on why that might be? First, there's a hard cutoff. If you try to do 1,000,000 k-points here, it wouldn't work, or some cutoff number. Maybe not 1,000,000, but more like 1 billion. Yeah.
Is it because Python manufacturer too small a number, in order to be a, the next step would be too small?
No. Not quite. I mean, that we are assuming that we have sufficient precision, that's not a problem. And we wouldn't hit that limit here because double precision is plenty. Yeah. Yeah. Yeah, go ahead.
Does it have to do with placing stuff into bins, or?
I'm not talking specifically about this code, much more generally with vectorization. And this might be useful for other things that you're doing as well. So nothing specific about what we're doing right now, but it's something good to know about in general. And the same principles are going to apply regardless, yeah.
So the matrix we are creating won't become the RAM.
So yeah, for the first upper bound is you'll run out of memory, right? So if you try to do this with too large of a chunk, you're going to hit an upper limit because you'll run out of memory. And we may have to sample to the point where we don't actually fit that entire data set in memory. And especially with Monte Carlo sampling, there's no need to. You can just do it in small chunks and average over it, that's better. The second issue is it's not enough if you fit everything on RAM. It's actually beneficial if you're fitting things on the cache of your processor, right? So if you work with too large of a chunk, you're ruining memory locality and you're actually making all the operations that much slower. So there's an optimal size such that your data sets are fitting on the cache, but are big enough that you're not running into an interpreter cost. So I'm not going to do that here, but you can play around with vectorizing this in different ways, and you'll see that there's a sweet spot in terms of when you don't run into the interpreter cost and when you're working with small enough data sets that they stay memory local and they take advantage of the cache. Okay, so did you guys already have some things on like performance tuning and so on in this course? You probably will have. I think it's a bit out of order in that sense, yeah. So you have some GPU programming workshop later, right? Yeah, okay. Yeah, you'll have similar constraints there too. All right, so regardless, so what we're going to do instead is we want to be able to control how much we are vectorizing over. So we're going to break this up into chunks, so or blocks here. So we're going to do this not as a single set of how many ever k points we wanted to do, which of course would work in this limited context. Instead, we are going to do a loop over blocks, and within each block vectorize the operation, right? So what I'll do is, so in order to do that, I need to accumulate my histogram over multiple runs. So I'll first create a, so let me copy this. So I'll eventually need to do the same operation, so I'll leave this normalization in there. But I'm going to do this n blocks times, so my effective number of k points is going to get multiplied by that. I'm going to loop over these blocks, and I'm going to do this calculation within that loop. Right? And here, instead of just doing this, I will accumulate my density of states, summing up over blocks, and I'll initialize that here. Right? And then I finally do that same normalization, just accounting for the total number of k points that I've gone over. And to address the second minor point of knowing how far this has gone, I'll print the block number I'm currently at. So that it'll give me progress, right? So then at least I have some patience in waiting, since I know how long it's going to take. So you can of course get better. You'll of course get a more converged result as you increase the number of k points in this. If you were willing to wait enough, I could probably reduce this further, but for the sake of demonstration, this is sufficient here, right? So now, if you notice the shape of what you have here, this is quite close to a parabola, a square root one. So this is very close to square root of energy starting from this point, which is what you expect for the density of states of free electrons, right? Because it has a dispersion relation of h bar squared k squared over 2m. The corresponding density of states would just be a parabola. So you get mostly that behavior, except you get some deviations where I mean, this may look, this is, if you converge this more, you can see that this is actually not noise. You get some corrugations there because of the band structure. Because what you have here is not a perfect parabola, you have these deviations from it. So all of these things create a change in the density of states. Right? So those are the features that you're seeing here.
Can you go back to the code for a minute?
Sure. Sorry, I did paste a bunch of things really quickly. Yeah. So yeah, while we're waiting on that, any questions on this idea? So you can later play around with this and for this or other computations, keep the total number of k points being calculated the same and change the number of blocks and the number of k points within the block. So that is the block size, and see whether there's an optimum in the time it takes. You will typically find that there is something such that the data sets are a few megabytes in size, which is what would fit in a typical cache. Once it goes beyond that, you'll start seeing a performance drop. But so in C++, it wouldn't matter how small you make your blocks. But in Python, if you make your blocks too small, you're going to get the interpreter cost. So everyone set with that? Okay, so yeah, and this is an easily, because this is Monte Carlo sampling, this is easily parallelizable. So you could use message passing interface in using MPI for pi or something like that and parallelize this. We are not going to do that here because that will just unnecessarily make it harder to run, not so easy to work with in a notebook. So we'll stick with this non-parallelized version and we'll focus on making the physics of this more complex. But if you're familiar with using MPI within Python, you can practice that as well, right? So you can run this more efficiently if you're not relying on threads, but actually relying on MPI to sum over k points. Okay, so now so far all our band structures and our density of states have been on this absolute Hartree scale, where I told you that this energy axis doesn't really have an absolute meaning. Right? So I could shift all the energies within the solid by something and it doesn't really change anything. Now, if you look at the band structure of a conventional material, for a metal, it is typically plotted relative to the Fermi level being 0, where the Fermi level is the energy up to which the electrons are filled, and then it's empty after that. So what we are going to do next is calculate the Fermi level for this particular density of states or band structure, and reference all our band structure and density of states plots to that. So effectively the idea is the Fermi level or the chemical potential is controlling the number of electrons. And for aluminum, we know that we have 3 electrons per unit cell. So what we are going to do is we are going to figure out at what point I should set my Fermi level such that the number of electrons below that integrates to exactly 3. Right? So what I'm going to do first is I'm going to calculate what is the number of electrons below each energy, right? And I'll do that by doing a cumulative sum on the density of states, right? So this will basically give me, it's adding up the density of states up to a particular level. To convert that to an integral, I just multiply it by dE, right? So this is going to be the total number of electrons up to a particular one, and this is basically going to correspond to, when I did my histogramming, I have these bin edges. It's going to correspond to the upper edge of each bin, because I'm accounting for all the states up, including that interval completely. So what I've not written any valid code here yet. What I'm saying is this number of electrons below is going to correspond to the energy that is at the end of each bin. So if you notice the code here, I created energy bins that go over some range, And then when I get the histogram, I'm actually plotting it with respect to the midpoint of each bin. I forgot to mention that code here. So I'm plotting it against E mid because in the histogram I have these intervals and I'm associating all the states within an interval to that range. The original bins I give it are the end points of the intervals. So I need to associate it to the midpoint of the intervals for making this plot. Now, the midpoints have one less data point than the bins because because of the intervals. But now here, when I'm looking at the cumulative sum, this effectively corresponds to the number of states including that interval. So it corresponds to the energy at the end of that interval. So that's why I'm looking at dropping the first one, which is the start of the first interval, and looking at the remaining bins. Right. So I've just written that statement there. What I need to do now is I need to figure out for which value of E bins is n below going to be equal to z val. Right. So I need to invert this. I need to find that value of n below for which, that value of E bins for which the corresponding n below equals z. Oh, one more thing. The density of states was per unit volume. So to get it per unit cell, I should multiply by the unit cell volume again. Okay, so how do I do that? So I want to calculate the chemical potential or the Fermi energy of electrons, inverting this. So I want to calculate the energy at which n below will be equal to z val. So I have a list, I have two lists of numbers, energies and the corresponding number of electrons below that energy. And I want to find what value of energy will give me exactly Z, the valence charge of 3. I could also potentially, you could see what this is going to look like. It's going to be a fairly smooth function. Right? So I basically want to do this graphical operation of finding 3 and converting it. My mouse is not moving smoothly. I want to find this graphical operation of finding the value 3 and then dropping it down to the x-axis to find the chemical potential. So programmatically, is there a nice one-liner that will do that? So one useful trick for doing these kind of inversions is to use interpolation. Because I have this monotonic function, what I'll do is I'll use the interpolation, and I want to interpolate to find what is the energy corresponding to Z val. I'll just make n below my x-axis, and I'll make my x values, and I'll make this E bins 1 my y-axis. So so I'm basically taking x and y and then interpolating that to this value of x. So that will just give me the energy corresponding to that value of Z. Oh, I shouldn't have removed that plot, but you can see that that kind of makes sense. So any questions about that? So effectively by using interpolation, you can figure out what that value is. I could have also done something where I just find the value that is closest to, find the value of n below which is closest to Z val and then pick the corresponding E. But by doing this, I'm also using the fact that this is a smooth function and I'm going between bin values and selecting that value of mu where my number will be equal to Z. Let me know if that makes sense. All right. Okay. So now that we have that, we can replot this density of states in terms of more real units. Specifically, due to that, we will now reference to this chemical potential and convert to electron volts, and we can convert the density of states to 1 over electron volts times nanometer cubed units, because it's per unit energy per unit volume. So then this will become that, and I'll also add an indicator for where my neutral Fermi level is. Okay, so that allows us to put the density of states now on a physical energy axis relative to the Fermi level of the metal. And whatever integral of the density of states you have under this are all the occupied valence electrons that you have in that material. Right? We could similarly also plot our band structure on this. I'll just put that code here as well because we'll keep using this again. So I'll refer it to the chemical potential and convert to electron volts units. That would be because I overwrote my energies with during the DOS calculation. So if I want to plot the band structure again, I would need to recalculate the energies here. And I'll similarly indicate the Fermi level to make things clear. Right? So this is now much more like a band structure you would see published for a given material. So this is once again for aluminum. And I'll remind you about this parabolic region here, which effectively corresponds to a free electron-like band structure. But the fact that it deviates from the parabolas, all these splits that you get here, are results of perturbations from that perfect free electron gas due to the atoms present in the, due to the nuclei present in the material. Okay, now also we are going to next calculate the optical excitations in this material, and we are particularly going to focus on the vertical transitions. So remember that if this had been a free electron metal, you would not have had any of those. It's precisely because you're deviating from these free electrons that you can do all these vertical transitions here, connecting from something below the Fermi level to something above, giving you a hole here and an electron there. So what we're going to do now is calculate the probability of that. And we're going to calculate the probability of doing such a transition, and we are going to calculate the probable energy distribution of electrons and holes you get after you do this excitation, like the results I showed you in the slides yesterday. Okay, so we are going to do that using Fermi's golden rule for calculating the rate of the process. So we are basically going to have the rate of that optical excitation, which is given by the matrix element for the electrons interacting with light, and it happens to be the matrix elements of the velocity, or equivalently the current or momentum given here. So this is the expectation value of the current operator at a particular k between the band B and B prime, right? And the reason why you get this is effectively the coupling between electromagnetic waves and these electrons is through the minimal coupling, so it's an A dot P type coupling, for those of you who are familiar with that from QFT. And you get the same kind of behavior here, or you can think about it as the electric field coupling with the dipole. You can show that it's equivalent. And so it's the vector potential dot product with this velocity which is giving you this behavior. So that's the perturbation here, the velocity squared. Apart from that, you have these occupation factors that tells you that you have a state available, an occupied state available for the initial state, and you have an unoccupied state available for the final state, and you have to conserve energy, right? And the fact that you need to conserve momentum is built into the fact that my initial and final states are at the same k, because we are effectively neglecting the photon's momentum from the beginning. All right? And apart from that, you have all these prefactors like the spin degeneracy and the number of k points you do to do the sampling and so on. All right? Once you calculate the absorption rate, you can write that as an imaginary dielectric function. So those are also included in this prefactor. Okay? So I won't be deriving this expression because it's going to take some time, but we'll focus on figuring out how to calculate these kinds of properties using the Warnier representation that we have. Right? So first, we already have the energies, and from the energies we can calculate the Fermi occupations. But what we don't have are the velocity matrix elements. So we need to get that into a form that we can use. And our velocity, since we are working in atomic units, the charge of the electron, mass of the electron, h bar, all of these are 1. So my velocity matrix elements are the same as the momentum matrix elements. So that's what I'm going to read in. So I'll start with just reading in the file as I did before. This would just be a list of numbers. Now I already know the dimensions, so I can just directly reshape. I don't have to calculate them again. So it's going to have, so if you remember, my Warnier Hamiltonian had this dimension. So I'm going to have the same thing, except I also have 3 components of momentum. So I have momentum in 3 directions. So I have an additional dimension here, which corresponds to that. So that's the order I've stored it in the file. Right? And like before, I have to account for the matrix order between the C code and this. And this, in this case, I will swap the last 2 axes, which would be 2 and 3. Of course, if I didn't get the product of dimensions right, this would have complained. Right? So these are the neighboring cells. These are the Warnier function 1 and Warnier function 2 that you're taking the overlap between. And these are the 3 momentum directions. Right? Now, when I did the Hamiltonian, I used the Hamiltonian, I Fourier transformed the Hamiltonian, and then I diagonalized it to get the energy eigenvalues and eigenvectors. When I'm doing this with the momentum, I'm not going to diagonalize the momentum operator. What I need is I need the momentum operator in the basis of the energy eigenvalues, because I need to know what are the momenta of each state, and I need to know what is the momentum expectation value between 2 states, because those are what will lead to transitions over here, or the velocity matrix elements. So I need to Fourier transform the momentum matrix elements, and then I need to unitary transform them to the basis where the Hamiltonian is diagonal. So these U matrices here are precisely going to be the eigenvectors that I get when I diagonalize the Hamiltonian. Okay? So what we are going to do next will require us to calculate this expression. So let me just temporarily make this larger. right? So we have, this is the matrix elements we just read in the Wannier basis, distance between the cells, Cartesian direction, two Wannier function indices, right? We Fourier transform it to a given k, the direction index is unchanged, and you do these unitary rotations to take you from Wannier functions to the eigenfunctions, right? Exactly as we discussed in the slides yesterday. All right, so any questions about that? Right? And we are going to calculate our dielectric function on a regular frequency grid. So let me just initialize this. Like we had an energy grid, we are going to use a histogram on this. So this just sets up a frequency grid with a resolution of 0.01 eV. And these are the edges of the bins and the midpoints, right? And what we are going to calculate should compare to this. This is the experimental dielectric function of aluminum as a function of frequency, right? Or photon energy. So the visible range goes roughly from here to here. Some 1 point something eV to 3 point something eV. Right? And because this is a metal, the absorption blows up as you go towards zero frequency. The dielectric constant goes to infinity at zero frequency. Alright? So this is what we need to calculate. Okay, so we are going to start with the density of states code again. So we're going to have that same blocked structure. So I will copy that over. So that's going to be our starting point. Right? And let me first test the code with 10 blocks before we jump to 100 blocks. And what we are collecting this time is going to be the imaginary dielectric function. So let me just let's do the easy things first. This is going to be on the frequency grid, not the energy grid. And I'm going to have to do some normalization, which we'll put in later. And this is going to be d omega, right? So some of these things will stay the same, so I'll just leave it like that. We'll have to adjust that later. Okay? So we're going to do the same thing. We are going to calculate we are going to do the Fourier transform of the Hamiltonian. We're going to get the energies, but this time I need the rotations as well. I need the eigenvectors as well. So remember, note that so far we have not used those unitary matrices at all. Right? This is the first time we're going to do that, because we are going to bring the momentum matrix elements into the energy eigenbasis. Right? But in addition, we need to also transform the momentum, we need to do the momentum matrix elements. So first we need to bring them first we need to do the Fourier, what did I do? So first we need to do the Fourier transformation, which will be exactly like the Hamiltonian. So if I take this dot product, this tensor dot product of the Fourier transform phase with P Wannier, that just does that sum over R minus R prime, and it gives me the momentum matrix elements now in K. So once I've done this, what is left to be done is to apply the unitary rotations. Alright, so now I'm going to introduce my favorite NumPy function here now. But so let me first show you what it would have been if this was just a single one, right? So if I just had one matrix and I wanted to do this transformation, if U was just a single unitary matrix, I could have now done, I'm just going to replace the variable P, I could have done this is U dagger, right? The transpose and then the conjugate, which gives me the dagger. I will multiply that with the dot product of P multiplied by U. Right? So this is what I want to do, physically speaking. But the only complication is I don't just have one matrix. I have it first of all for a bunch of K. I have it for 1,000 K points together over here. Right? And additionally, the momentum has three directions. right? So I effectively want to do this transformation for 3000 matrices together. All right? So we could, of course, just do a loop, pick up one matrix at a time, do a code like this and write it. The only challenges with that is it might become slow if these matrices are small, and it would be kind of hard to read because, you know, you're adding unnecessarily loops where they don't need to be. So the ultimate killer for writing vectorized code in Python is the function called einsum, which basically does Einstein summation convention in code. So this is what we're going to use. So I'm going to write this pseudocode that I've written here using this once again. So let me first copy this. These are the things that I want to multiply together are effectively this: U dagger, P, and U. By the way, how many of you are familiar with Einstein summation convention? Good. So it's fairly easy to pick up, so hopefully the rest of you will figure it out as we're doing this here. So writing this here is almost as easy as writing it on paper. I first just write out the dimensions. So what does U contain? So I'm going to use the indices similar to the expression over here. I'm allowed one letter per index. So I'm going to write out a string that tells me what I need to do. So first let me write out the final, let me write out P. P has a K index, it has a direction index, and it has two Wannier indices. Let me call it A and B. Right, so I'm just listing out, P is a rank 4 tensor. I'm listing out all its indices. U is a Wannier, it's a unitary rotation, but it's a unitary rotation for each K. So this has 3 indices, and I'm doing a matrix multiply here. So I will write it out as, let me say, K, B, and C. So if you ignore all the other indices, I'm multiplying PAB with UBC, and if I sum over B, I should get something that has the indices A and C. Right? That would be a matrix multiply. Of course, I also carry around the remaining indices here. And in that same shot, I can also do the multiply here. So U dagger will have KDA, let's say. And then that A is summed over here, and it gives me D here. So effectively I'm saying do a matrix multiply in those indices, do a matrix multiply in those indices, and just carry the K index without doing anything. And similarly carry the I index forward to the final result without doing any contraction. Now this is basically what we will do, except for one caveat. Transpose on this rank 3 tensor will do the wrong thing. So I will remove this transpose here and achieve the transpose just by swapping these indices. Because transpose will revert all the indices if I do it on a rank 3 tensor, which is not what I want. Okay, so I will only take the conjugate there, and the transpose part of it I'll just do it by swapping the indices in the string. Right? So the first line here is doing the Fourier transform, and the second line is doing all the unitary transformations that we require. So this is sort of the most important thing I want to cover in this module. So it's a really versatile function. So if you have, just think about that for a second and let me know if you have any questions. The remainder of this is fairly straightforward of this particular tile. Have any of you used einsum before? Okay. Do you like it?
It's amazing.
It's the best, right? Yeah.
It's absolutely incredible.
Yeah.
It can get slow though for big transformations.
Yes. Yes, we'll get to that in a subsequent one if we have time. Yeah. But actually, if you break it up into smaller bits and you're always doing one index contraction at a time, it actually calls the blast function, so it's pretty fast. Yeah. Okay, so let's go forward. Just if you have more questions about it, think about it, and please do try playing around with it to do other things. You can write fairly complicated linear algebra operations in a single line using it, although you shouldn't always, as we just said. Okay, so what do we need to do next? So this gives us the momentum matrix elements in the basis of the eigenfunctions, provided we did that correctly. Now we need to take, let's go back to the expression here, over here. So we take the absolute value squared of that, and we need to do the following operations. We need the Fermi fillings, so we need to calculate the Fermi occupation factors, and we need to do this energy conservation. Okay, now because there is always going to be exactly one frequency which is going to be energy conserving with a pair of electronic states, instead of writing out this delta function, I'm going to do this delta function as the histogram. So every contribution will correspond to a particular energy difference, and I basically collect that in a bin corresponding to that frequency. Right? So that's what my histogram is going to do. So I don't need to worry about this energy conservation for the moment. But I need to know what pair of energies each thing corresponds to. So now I have these matrix elements that are at each k, they're giving me two bands. So I need to do the same thing with the energy difference. So first, I'm going to do the frequency for each pair. So I'm going to have an omega, remember h bar is 1, which gives me the energy for each k point. For the first band with a dummy index there, and I'm going to take the energy difference against that. Okay? So this is the free, so this will now give me a rank 3 tensor which corresponds to every k point and the energy difference between pairs of states at that k point. Right. Now I need to calculate the occupation factors corresponding to that pair. So first I can just calculate the Fermi occupation factors, which I'll just write out the expression for that. What did I do? Right, and I think I should put, I'll put kT equal to 0.001, that corresponds roughly to room temperature in atomic units. Right? So those are my Fermi occupation factors. And then I will calculate the difference between the initial and final state fillings, which is what I had in that expression, in exactly the same way, except that I have it the opposite order. Yeah.
What's the other one?
Say it again?
Before you did, what's the one? I thought you put something.
Oh, it's just my cursor probably.
Oh, okay.
Yeah. Right? So this now gives me the difference between the initial and final state occupation that's present in Fermi's golden rule, and I have all the pieces. I have the matrix element here, which I'll take an absolute value squared. I have this, and then this is telling me where to put that contribution for histogramming. So I'm going to do that here. So let me calculate a weight associated with each transition, which is the absolute value of P squared. And I'm also going to sum over the direction index. Right now I'm assuming an isotropic material. Right? So the second index of P is the Cartesian direction. So I'm going to square over that. So that's the vector mod squared here. So I'm going to sum over the second axis. Right? So this is the matrix element squared in Fermi's golden rule, and that is going to be multiplied by F diff. So this is the weight of the transition, and now this will get associated with the frequency I'm histogramming it by that frequency grid, and I have to give a weight associated with each transition, which is this, also flattened. And that's basically it. So I mean the hardest part of it was just figuring out the matrix element. And finally we need to sort out this prefactor. So let me look at that expression again. So I have 4 pi squared gs, so that will be 8 pi squared. E is just 1 in atomic units. And I have 3 omega squared in addition to what I already had. So my prefactor here is going to be 8 pi squared and 3. And I also have omega squared, which is going to be that. Right, and then I have the nk, the total number of k points, the unit cell volume, and the converting it to a probability density that we wanted to do. Alright, so let's run that, and I'm sure that's going to have some errors which we'll have to fix. Or maybe not. Surprisingly not. But let me just run that for longer and I'll leave it on the code. Okay, so the operations I did was figure out the matrix element, first doing the Fourier transform, then doing the unitary rotations to bring it to the eigenbasis of the Hamiltonian, right? And after I did that, in calculating Fermi's golden rule, I had the difference between the frequencies, the difference between the energy. So this is energy conservation effectively, because I'm taking this omega and histogramming it there. I have the difference between the occupation factors. That's telling me that I have my initial state occupied and my final state empty, right? And I just do that, put in the prefactors that connect from the absorption rate in Fermi's golden rule to the dielectric function, and that's the result. Right? And remember that although I didn't show you how we did it, the calculation of the Wannier Hamiltonian and so on you've been using don't have any experimental input, right? They're purely from saying that this is my crystal structure, these are where my atoms are, these are the charges on the nuclei, figure out what, solve the Schrodinger equation for the electrons, and we're starting just from those laws of physics and predicting this experimentally measurable quantity, right? Now, it agrees really well in this energy range, but we are overestimating the experimental result here and then underestimating it here, completely not capturing this blowing up to infinity. Right? So now why is that? Potentially at very high energies, yes. So this could be because you could have multi-electron transitions and so on. That's right. But what about here? So the phase space for doing higher order processes decreases as you go down to 0. So it's very unlikely that a higher order process, a higher order multi-electron excitation process would have a higher probability here. So remember that this is only one of many mechanisms. So this is the mechanism where you're only allowed to do vertical transitions. So what's happening here is you don't have that many possibilities for doing these vertical transitions. So the next best thing, which is using a phonon to pick up momentum, becomes important. And as you go close down to 0 energy, that becomes a dominant process, because you have a very large phase space for picking up momentum from a phonon and moving at the same energy, which you cannot do unless you had an external source of momentum. So the phonon assisted optical transition that I'd mentioned in the slides, but which we have not calculated here, is responsible for most of this remainder. Right? So in the results I showed you yesterday, by adding that process, that worked out quite well. But that still doesn't explain how I can have this peak that goes above the experimental results here. So the second thing that's missing here is the carrier broadening. So here I'm assuming that every electronic state is infinitely long-lived. What's going to happen instead is, instead of having this delta function where I have exact energy conservation, I will have a Lorentzian broadening with a particular width that corresponds to how short-lived, what is the energy broadening associated with each carrier. So once I account for the fact that high energy carriers in the material have a finite lifetime, that will broaden these contributions, and that will also improve the agreement with the experiment there. Right? So there are a number of effects beyond this basic one that are required to get a much better description of the dielectric function, but hopefully it's illustrative that by doing something fairly simple, starting from this Wannier Hamiltonian, you're able to calculate a relatively complex material property. Yeah?
So, this is still a dielectric function, it's just for vertical transition.
This is the contribution from vertical transitions to the dielectric function. Yes. Yeah. So there are other terms coming from the Phonon mediated process which are not included in, which are of course included in the experiment but not included in what we've calculated. Okay. So what we'll do next now, so as we said, this is great. This gives us some confidence that we have good agreement with the experiment here, but we can now ask the next question, which is, once you have, so this is absorption in the material, right? You have absorbed light to produce an electron hole pair. So now we can look in to see what are the energies of the electrons and holes that are produced from this. So what we'll do is, we'll copy this code over, but instead of just collecting only the total contribution, we will also collect the contributions based on the energies of the electron and holes in each of the transitions. Right? So let me start by copying this entire segment over. Right? And what I'm going to do now is I'm additionally going to collect these dielectric functions resolved by electron and hole states. And these are now going to have not just the 0 to omega, but they are two-dimensional functions. For each photon energy, I'm going to calculate the probability distribution of electron energies and hole energies. Right? So this part of the code is exactly the same, but now I have to change what I'm histogramming here. So this, so far, so I'll keep this code there. So now I'll do the carrier distributions here. And once again, let me start with a few blocks to get this started, so we can test it. Okay, so I need to, what I'm going to collect is the 2D histogram based on the frequency of the transition and the energy of the electron relative to the Fermi level, and separately I'll do it for the energy of the hole relative to the Fermi level, right? So I'll have the energy of the electron with respect to the Fermi level. Let me just say this. So it's going to be E minus mu, because this is going to be above the Fermi level. And I'm going to repeat this for every other state. So this is going to give me the electron energy associated with every transition. I'm similarly going to calculate the hole energies associated with every transition, and that's going to be mu minus that. Right? Basically, so this was the electron energy, this was the hole energy associated with each transition. So I'm taking this relative to mu here for that n bands by n bands matrix, and I'm looking at this relative to mu here and just changing the order so that it's positive. Right? So these are the things I'm now going to histogram as the second axis. So then I can collect this, which is going to be a histogram 2D with the frequency as the first axis and the electron energy as the next axis, and the weights that I'm going to use there are going to be the same. So the event weights are the same, it's just that I'm histogramming by one additional quantity. And I can do the same thing now for the holes. Okay, and then I'll have to do the same normalization factors here. So let me copy this over. Right? So let's start with that and see what it looks like. So these are now the imaginary dielectric functions resolved by carrier energies. I'm going to make one more difference to this, which is when I do this, I'm going to have the overall probability density that I get an electron and hole, including the absorption of the photon. Instead, for plotting the carrier distributions, let me think about the conditional probability that I've already absorbed the photon. What is the energy distribution of energy and holes? So I'll normalize this by the total IMEPs at that frequency. So I'll define another normalization factor for the 2D histogram, which includes the first one, and then it divides the integral over carrier energy, which is just IMEPs. Right? And I'll need to broadcast it to add a second axis. Okay? So yes, the only issue with doing that is some of these might be 0. So I'll put a lower cutoff here, so that if it's 0, it doesn't do a divide by 0. Okay, so you can begin to see some things here, but you see a lot of, you can see a faint outline of a triangle, maybe not on the projector, but you can see mostly points focused in here. Now the reason for this is, when I am at a low photon energy, I have very little omega range over which, very little energy range over which I can produce a carrier. So my probability density in that energy window is going to be very high. So I'm going to get a very biased probability distribution, which is going to be very large here and very small there. So I know that if I had a uniform carrier distribution, my probability density would just be 1 over omega flat. So what I'll do is I'll redefine my probability that I'm plotting. I'll redefine my probability by multiplying this by the frequency. Right? Such that if I have a uniform carrier distribution, it will just take value 1. And if it's non-uniform, then you'll have some regions greater than 1 and some regions less than 1. And that way you'll be able to see it across the energy range much more reasonably. Right? So now you can see that you get these dots all over the place, but the main problem is, at least with the runtimes that we are willing to take here, you have very little data. If I was to run this for a factor of 1,000 more blocks, you might fill this out. So for the purposes of seeing something reasonable here, let's smooth it out a little bit so that we get a slightly smoothened histogram here. So I can use Gaussian filter to do this really easily. And I can do the same for the holes. Right? And you get a carrier distribution like that. So it's effectively just taking that data and setting it up over this. And I've clearly missed some multiplicative factor in my prefactor. I guess I forgot one factor of d omega that needs to come because it's a 2D histogram. Oops. Yeah, so now it's roughly in the order 1, so that's correct. And while we are looking at the code and discussing, as before, let me run this for more. Okay, so what I basically did was compute the energy relative to the Fermi level for the electron and hole associated with each event, right? And then do a 2D histogram based on that, and then just normalize it appropriately such that it gives me 1 if it's a uniform carrier distribution, and that is what I'm plotting here. And I plot that using IM show, and there's some jugglery here to have the correct orientation. You can look at IM show's documentation to do that. I did not choose a 3D plot here because it doesn't work well within the notebook, but this is basically the same as the plots of the carrier distributions I was showing you yesterday. So aluminum with direct transitions gives you a mostly uniform probability distribution. You can see this color corresponds roughly to 1, but there's some speckle pattern here that is of course the finite sampling of our Monte Carlo right now, but you can also see that there are some features here which are not Monte Carlo noise. Right? There are certain spots here where you don't have carriers, right? And then even here, there are some dips here where you don't get any carriers. So can you speculate as to why that is? So why is it an almost uniform distribution but not quite? Specifically, maybe you can speculate as to why you have these missing triangles here. So this is basically telling me that when I absorb a 4.5 to 6 eV photon in aluminum, I will not get any holes that are exactly at the photon energy, and I won't get any low energy electrons in this range. All my electrons will be above. So you can look at let's go back to the band structure. Okay. If you look at this carefully, you will find that the location where this happens is right around where this band ends. So most of the uniform carrier distribution is being given by transitions across this. So when this band flattens out, you suddenly lose an energy channel there. You can continue following up this, but you will get a lower energy hole, and you will not be able to get a hole which is in that 5 to 6 eV range, because there is nothing that this can transition to. And that lack of states is what shows up here. And similarly, there is some level splitting that occurs here, which makes it such that there is no state available in that very narrow window. Right? So all those features in the band structure show up here. In the case of aluminum, it overall still looks very flat. If we did the same thing for gold, which of course would just amount to plugging in the Varnier functions and just running the same codes through, you would see a wildly different pattern which focuses the distributions on specific energies, which have to do with the d-electronic states that are present in gold, like we were discussing yesterday.
Can you just go back to the above code for a second?
Yeah. So while we're waiting, any other questions? So we'll go through and do phonons in the same way, but looks like we won't have time to do the electron phonon properties. So I'll just sort of talk you through it, and if you're interested, you can look at it offline. Just run through the notebook with that. Of course, you have the completed notebook separately where you can just look at the final code. Exactly like we did the electronic band structures with Fourier functions, we can do the analogous properties for phonons, and in this case the role of the Fourier functions are taken by the atoms themselves. So effectively you will now write the phonon Hamiltonian in terms of I move an atom in this unit cell and I look at the force on another atom in an adjacent unit cell. Right? And when I diagonalize that, when I Fourier transform and diagonalize that, I will get the phonon frequency squared. So the only subtlety is you don't get the phonon frequency, you get the square of that. Right? And this has to do with the fact that it's a massless boson. Right? So the form of the dispersion is different. So let's look at the phonon cell map, which is a file exactly like the Fourier cell map that we were looking at before, and we can read it in quite the same way. Right? We can read in and reshape the phonon omega squared file the same way. So I'll do that. Oh, scrolling is going to take a while. Right? So I'm going to read in this omega squared file, which I'll call it omega squared r for being in real space. Right, and I'll call this the number of modes, or which are basically the number of normal modes per unit cell associated with the phonon. And then I can reshape this in quite the same way. Right, so I have aluminum has one atom per unit cell and it can be moved in 3 directions. So there are 3 modes of perturbation associated with every unit cell. And this time I have a much more short-ranged interaction. So instead of the 2000 odd cells I had for the Fourier, I just have 93. Right? So the range of the phonon force matrix is much smaller than the electronic Hamiltonian. Right? And once I have that, I can copy over my band structure plot exactly as before. Right? And everything remains exactly the same. I just use the different cell map. I Fourier transform this instead. And I'll get omega squared when I diagonalize it. And then if I take the square root of that, I'll get my phonon frequencies. So you'll sometimes get some numerical errors that make things slightly below 0, and you'll get a bunch of warnings. So I'll just suppress that by cutting off any omega squared that go below 0 to 0. Right? And in exactly the same way, you can plot phonon band structures as we did electronic band structures. Right? Now there are some qualitative differences here. First, when you go close to gamma or k equal to 0, you don't have a quadratic dispersion anymore, you have a linear dispersion, which corresponds to the fact that these are massless particles. Right? You also have an absolute energy scale. Now 0 is absolutely meaningful, so you do have 0 phonon energies associated with the bottom here. right? And the slopes that you have right here correspond to the sound velocities, because these are the low frequency, the long wavelength oscillatory modes here, right? So the highest one here correspond to longitudinal sound waves, which is what you're used to, and the lower ones are transverse sound waves, right? And the other important thing is the energy scale. So our electronic energies are on the order of 0.1 to 1 Hartrees, and our phonon energy scales are now about 2 to 3 orders of magnitude smaller on the 0.001 Hartree scale, right? So instead of, or if you want to look at it in electron volts, it's going to be so let me write this. So if you looked at this in milli electron volts, this would be on the tens of milli electron volt scale, right? And room temperature at 300 Kelvin, kBT is around this value. So for aluminum, the phonon energies are sort of just about straddling room temperature. So at room temperature, most of these phonon modes will have quite a significant occupation, right? So they will all contribute to things like electronic resistivity. All right. Yeah, we can do the same thing for density of states, but I'm not going to do that in interest of time. Okay. So since we are right about at time, I'll stop here. Let's just let me know if you have any questions here. I'll briefly discuss what the outline of the remaining part is, and then you can follow through it later. So what I do, so when we want to calculate the electron phonon matrix elements, we now are no longer working at individual Ks. We are coupling all pairs of K points with each other. So what the code does is it first packages whatever we did so far for electrons and phonons into convenience routines, right? And then the electron phonon matrix elements require the computation of this quantity, where you have a similar Fourier transform and unitary rotation as we've done so far, except for the fact that the phonons now break translational invariance of the crystal. So in this Fourier transform, it is no longer r minus r prime. You have a different k and k prime, and you have a k prime dot r prime minus k dot r. So you have to do a double Fourier transform over r and r prime. So the phonon force matrix cells are going to have that. Then the unitary transformation parts here are the same, except that one is at k and the other is at k prime. Right? So then the inner part is familiar. In addition to that, you have an extra unitary rotation which takes you to the eigenvectors of the phonons, and you have an overall normalization which has to do with the phonon amplitude. Right? So that's what you need to do theoretically. And the code for that is this lovely segment with a bunch of einsums. Right? So but if you dig through it, it's actually fairly straightforward. I was not planning on doing this here anyway because it would take a while to write, right? So effectively you go from the bottom, you start from the original one, you do the first Fourier transform, you do the second Fourier transform, you do the phonon rotation, one of the electron rotations and the other electron rotations for all pairs of K points bands together, and then finally do the phonon amplitude, right? So in principle, it's quite simple, right? After that, what we need to calculate for the electron phonon scattering are these expressions, which are once again Fermi's golden rule, but you have to go over the electron phonon matrix elements. You have phonon occupation factors, electron occupation factors, and so on. Come to think about it, I don't know how I was planning to get through all of this in this 1.5 hours. But what the code does is it first collects this Eliashberg spectral function, which is one particular combination of these matrix elements and the energy conservations that you have. And then you can compute the conductivity at all different temperatures by doing an integral over that spectral function and the phonon occupation factors. So you can run through the code that's present in the completed notebook, and what it will show is you can actually predict the resistivity of aluminum also to quite a good accuracy compared to experiment, including its temperature dependence once you do all of this. Okay, so I'll be around here for questions. Thank you all for your attention.